So today I'm going to tell you a little bit about how high order moment and cumulant information can tell us, we'll learn how what it can tell us about learning causal structure in linear non-Gaussian models. Okay, so let me first tell you a little bit about causal models. So these are very useful across the sciences. So for example, they're useful in gene regulatory networks where we would like to learn how expressions of one gene, the expression of one gene can influence the expressions of other genes. And the way we model this is by placing the different genes at the vertices of a graph. And then we have directed edges whenever the expression of one gene influences the expression of another gene. And then here's another example for disease diagnosis where we would like to measure how different behaviors and different environmental factors can cause different diseases and how those diseases can cause different symptoms. And we place all of these variables at the vertices of a graph, and then we would like to learn the directed arrows. So what causes what? And what we would like to learn is the structure of the graph from observation. So for example, imagine we have 1,000 patients and we would like to, we measure all of this information about each of them, and then we would like to learn the causal structure, right? So let me give a more formal definition of these causal models. So today I'll be working with structural equation models, also known as structural causal models. So such a model consists of a directed acyclic graph, or a DAG, G, which has vertices V and directed edges E. So these are arrows from one vertex to another. And we have one random variable for each vertex. So X, V are the random variables, like all the diseases and so on. And then there's the directions, the arrows tell us when one variable influences another. And then the structural equation model comes with a set of equations that express each variable as a function. So xv will be a function fv of its parents and some noise. So what are the parents of a vertex? Those are all vertices that have an arrow towards the vertex. So everything that has a direct cause of that vertex. So each variable will be a function of the parent variables and some noise. And the important thing is that these noise terms are actually independent. So they're mutually independent random variables. Okay, so here's an example. We have this graph. So x1, so you have 5 variables, right? So x1 is just going to be f1 of some noise epsilon1 because this vertex has no parent, so nothing is pointing to it. So it's just a function of the noise. x2 is also a function of the noise because there's no parents of x2. Then there's 3 has one parent, 2. So x3 is f3 of x2. And 4 has 3 parents, 1, 2, and 3. So x4 is a function of those 3 variables and epsilon 4. And similarly for x5, which has 2 parents. Okay. And again, the question is, given samples from this model, can we identify the graph? And so what are the samples? So each of these x superscript I is a random vector. Is a vector. It's a sample. So, in this case, it would have 5 entries, and then we have n such vectors. And we would like to, given this information, learn the graph G. Okay, so this is the basic question. And so today I'll be talking about a specific type of structural equation models called linear structural equation models. So here, all of these functions fv are going to be linear. Right, so here's this example, but now everything's linear. So what this means is that each x v is a linear combination of its parents and the noise, right? So x1 is going to be a constant times epsilon 1, and we might as well just subsume the constant into the noise. So x1 is just the noise, epsilon 1, x2 is also the noise epsilon 2, and then x3 is a linear combination of x2 and epsilon 3. x4 is a linear combination of 1, 2, and 3, and 4, and epsilon 4, and so on. Okay, and so in general, for general DAG G, the linear structural equation model corresponding to it consists of the graph and these linear equations. So xi is the sum over the parents of some coefficient lambda ji times the parent xj plus the noise term epsilon I. And again, these epsilon i's are independent. All right, so we can actually write this in matrix vector form. So the vector x is going to be equal to the matrix lambda transpose times the vector x plus epsilon. So here lambda is a matrix which has zeros everywhere except if there's an edge from I to j. In that case, the entry lambda ij is non-zero. It's one of these coefficients. And because this sort of is a weird expression here with ji, we need the transpose. So that we have ji instead of ij. Okay, and equivalently, so we can put this term on the left. So we're going to have I minus lambda transpose x equals to epsilon. And if we invert it, then x equals to I minus lambda inverse the whole thing transpose, or you can first take the transpose, then the inverse times epsilon. And so this minus t is just denoting the inverse transpose. Okay, so either way you want to take it. And the important thing is that lambda has this special form coming from the graph, right? So it's 0, lambda ij is 0 if there's no edge from I to j, and epsilon is a vector of independent terms. Okay. Oh, and I forgot to say that, okay, because the graph G is acyclic, this matrix I minus lambda is always invertible. And the reason is that, so lambda is strictly upper triangular if you order the vertices so that all arrows go from a smaller number to a larger number. And so then I minus lambda is upper triangular with ones on the diagonal, and so it's invertible. Okay. All right, so this is the setup. And first, I want to tell you about what happens if the variables are Gaussian, and then we're going to see what happens if they're non-Gaussian. Okay, and the interesting thing is that it's actually harder to learn the graph if they're Gaussian, or you actually can't really learn the graph uniquely if they're Gaussian, but you can if they're not Gaussian. Okay, so if they were Gaussian, then xi is a linear combination of its parents plus epsilon I, and here epsilon has to be a Gaussian random vector. So it has some mean mu, and actually we're going to assume these are all 0, so let's just ignore the mean. And it has covariance matrix omega, which has to be diagonal because the epsilon i's are all independent. So then the covariance of epsilon is diagonal. Okay, so so again, we know that x is this linear transformation of the noise, right? So it's I minus lambda inverse transpose epsilon. And so this means that we can actually, so this means, first of all, that x is also Gaussian. It's a Gaussian random vector. So it has some mean, and again, let's just say it's 0, and covariance matrix sigma. And sigma is actually also a transformation of the covariance of epsilon. So, because x and epsilon are related like this, then sigma equals to I minus lambda inverse transpose omega I minus lambda inverse. And so now suppose that we get some samples, right? The x superscript i's, and then we can form a sample covariance matrix. And then we might be wondering, does this sample covariance matrix come from this graph? Can it be written like this? Okay, so all the Gaussian distributions that arise from a specific graph G can be expressed in this form. Okay, and so we actually denote by mg the set of covariance matrices, or we call it the set of Gaussian distributions that arise from a Gaussian linear causal model with DAG G, and we call this the directed Gaussian graphical model corresponding to G also. And really, it's all covariances that can be parameterized in this way. Okay, so again, lambda, so this is new notation here. So lambda has the structure of the graph, so it lies in R to the E. E is again the edges, so it means it has 0 if lambda ij is 0, and it's there's 0 if there's no edge from I to j, and otherwise it's some coefficient lambda ij, and then omega is positive definite diagonal. So the directed Gaussian graphical model corresponding to G is this set of covariance matrices. And really, because we are working with Gaussians, this specifies precisely when a random vector comes from this model. Okay, because the covariance matrix for a Gaussian describes other than the mean, it describes everything about the model. Okay, and so here's this graph that we had from before. The parameterization of the covariance matrix can be written like this, right? So it's I minus lambda inverse transpose omega and so on. And then lambda has this form. So it has zeros if there's no edge, and otherwise it has some entry. And then omega is positive definite diagonal. And the interesting thing that happens is that it's possible that two graphs give rise to the same model. And such graphs are actually also called Markov equivalent. And so if you have your sample covariance matrix, maybe you can tell which sort of model it comes from, but you can't quite pinpoint the graph precisely because oftentimes two graphs give rise to the same model. Okay, so we can only identify the graph up to what's known as a Markov equivalence class. Okay, and these Markov equivalence classes actually correspond to conditional independent statements. So there's another way to define these graphical models and via conditional independent statements. And it turns out that different directed acyclic graphs can give rise to the same sets of conditional independent statements. Okay, so this is in the sense in which learning the graph for Gaussians is hard. It's because you can't actually learn the precise graph. And so what happens is that if you have a non-Gaussian linear structural equation model, you can actually learn the graph uniquely. And that's quite interesting. And before I go into it, let me say that if you don't assume linearity, so if it's just a structural equation model, people usually look at, again, conditional independent statements. And they can, again, only learn the graph up to Markov equivalence. So this case of non-Gaussian linear structural equation models is quite special in the sense that we can learn the graph uniquely. All right, so let's see how it works. So here is, again, our equation. X is this linear transformation of the noise, and lambda comes from the graph. And so there's a problem called independent component analysis, which solves a very similar problem. So we're given that the random vector x is some linear transformation of a random vector epsilon, which has independent components. And you would like to learn this linear transformation A. Okay, so this is really a very similar problem because here instead of A, we have this matrix I minus lambda inverse transpose. And again, we have the noise term vector epsilon. And we would like to recover A. And of course, we can't really recover it uniquely. We have to do it up to permutation of its columns, because if you permute the columns of A, that's the same as permuting the noise terms epsilon I, right? So we can't really know what their order is. And also up to scaling of the column. So scaling a column means scaling the corresponding epsilon I, and of course we don't know the scale. But up to these transformations, we would like to recover A. And it turns out that if at least two of the epsilon j's are Gaussian, then you can't recover A uniquely. And that's because if you take two independent Gaussians, there's infinitely many transformations of that vector that will preserve the independence. So there's a lot of different ways to make linear transformations of Gaussians that will remain of independent Gaussians that will preserve this independence. And but if all but one of the epsilons are non-Gaussian, then A can be recovered uniquely up to permutation and scaling. So this is the very interesting part. So this problem has been well studied, and one can learn this matrix A in theory. And so there's a lot of different ways of solving the ICA problem. And I want to pinpoint this one here, which is actually via tensor decomposition. I'm not going to talk about this today, but it's very related to our long program. So if you take the fourth order cumulant tensor of this vector x, which I will actually define later, it turns out that its CP decomposition is the sum over I from 1 to the number of columns of A of some constant times this column of A to the tensor power 4. So it really decomposes into the columns of A. So if you do this decomposition, then you can find A. right? So that's one way of solving this ICA problem. And this is especially good if A is square. So then so it's sort of a low rank tensor. Okay. So basically, the first paper that was trying to learn such a linear non-Gaussian acyclic model like this was in 2006 by Shimizu et al. And they realized that they could use ICA methods in order to estimate this matrix I minus lambda inverse transpose. And the thing is that this problem has more structure than just, this is not just any matrix A, it's a matrix that is the inverse of a very sparse matrix. And also when you get the estimate, it will have a lot of entries that are not quite zero, and you have to decide what the threshold is in order to figure out when to call an entry zero. And there has been a very long line of work. And here I'm only citing 3 papers, but there's actually tens of papers on this topic. I want to talk about one of the latest ones by Wang and Durton, where they have a high dimensional algorithm where they have, you can actually estimate, these parameters, even if the number of observations is less than the number of variables. And what's really interesting to me is that it looks at relationships between the second and third and higher order moments of the vector x. So it looks at these high order moment tensors, and their entries have relationships that actually help you learn the graph. And so here is this very nice example of these. So think about these two models, right? Does 1 cause 2 or does 2 cause 1, right? And so if you look at and assume that both x1 and x2 have mean 0, then in the first case, this equation between the second and third order moments is 0, right? So we have, this is the second one, and this is the third order moment. And in the second case, this equation is actually non-zero. And of course, that's generically, right? So it has to be generic in the sense that this equation is non-zero. And in particular, if your vector was Gaussian, then, so for Gaussians, all the third order moments are 0. So these guys here would be 0. And we're assuming, again, mean 0 vector. And so this will be 0 for Gaussians for sure. But then if they weren't Gaussian and they didn't specifically satisfy this equation, so this is what the genericity means, then this would be non-zero. And so what they do is they, of course, these are simple graphs. So they have an algorithm that tests similar relationships over and over again in order to identify the graph. Okay. And so one of the things that I've been working on recently, and so this is still ongoing, is trying to identify all of the relationships that hold among the second and, let's say, third order moments, and maybe potentially being able to get a better algorithm. So let me just tell you what we've done so far in this case. So we're going to, so remember for Gaussians, the model was just given by all covariance matrices, kind of like this, that come from the model. But now we're also going to record the third order moments. So we're going to look at all S and T, where S is an, V, there's N entries in V. So S is an N by N matrix and T is an N by N by N tensor. So these are the second and third order moments of a random vector that comes from this model. And they have to factorize this way. So this one we already saw. So it doesn't really matter if your variables are Gaussian or not. The covariance in a linear structural equation model always factorizes like this. And the third moment will also factorize. And so let me explain what this means. So T is the third moment of X. And it equals to, so omega 3 is the third moment of epsilon. And then you have to do a Tucker product with I minus lambda inverse along each of the 3 modes. All right, so this is the this is what the third moment of X is. And so this T also has structure because omega 3 is a diagonal tensor. It's a an n by n diagonal tensor. And lambda, again, comes from the DAG, so it lies in R to the E. And of course, again, this covariance is the same as for the Gaussian case. So it's S is I minus lambda inverse transpose omega, where omega is positive definite diagonal times I minus lambda inverse. Okay, so we studied this set of second and third order moments, and we show that this set actually, so it's an algebraic variety, and we can find all of the equations in the case when this DAG is a tree. So if you remove all directions, then the underlying undirected graph is a tree. And these are very nice equations because they're just some of the entries of S and T have to be 0, and certain 2x2 determinants of a matrix have to be 0. So I'm not going to show you the actual equations in the interest of time, but I'm very happy to tell you about them later. But yeah, so it's given the equations are exactly these quadratic binomials, exactly like this here. So these are, quadratic binomials. So these are quadratic equations that have two terms, and it's the same here. So here's this matrix that has entries in S and T, and its 2x2 minors are 0. But I don't want to explain to you how we get this matrix right now. Okay, but so nevertheless, we're still quite interested in learning these equations for general DAGs. And then one very interesting question is what happens if there are cycles, because then we can try to learn a cyclic graph, which is, in the same way as the paper by Wang and Durton. So this would be a very interesting thing to solve. Okay, and so now let me talk about hidden variables. What happens if now there are hidden variables? So imagine that this variable 1 is now unobserved. And so we have, so this variable 1 exists here in the equation in all of its children, right? All of its children have it expressed here. And so what's going to happen is that these red terms will be subsumed into the noise. Okay, so right, so now epsilon4 and epsilon5 are no longer independent noise terms. Now they are these epsilon4 tilde and epsilon5 tilde, and they're dependent. All right, and so we have a graph with 4 vertices, 2, 3, 4, and 5, and we still have these linear equations, but the only difference is that the noise terms are not always independent. And graphically, we're going to place a bidirected edge between 4 and 5, and this graph has vertices V, directed edges E, and bidirected edges B. And in the equation, the epsilons that come for vertices between which there is a bidirected edge, their corresponding epsilons are not going to be independent. Okay, and so what happens is previously this is just an example for the covariance, and of course all the high order moments will have a similar structure. So this was our the parameterization of the covariance in this case, but in this case now we have the same parameterization where lambda comes from the directed part of the graph, r to the e, where e is now this new graph that doesn't have the vertex 1. But omega is no longer just a diagonal matrix, it lies in PDB. So B is the set of bidirected edges. So it has zeros on the off-diagonal entries unless there is a bidirected edge between the vertices, in which case it has a non-zero entry. Okay, so this is sort of the new our new setting now, where we have hidden variables. And it could be more complicated as well, because maybe one variable causes 3 or more variables, right? So let's say 1 is hidden, but it has more than 2 children. Then again, our equations are going to look like this. So x1 is gone, and x2, x3, and x4 are just some noise terms, but they're now dependent, and they're still independent from epsilon 5. Okay, and so this new structure graphically will be represented by vertices, directed edges, and multi-directed edges. So this new graph is going to have multi-directed edges H. And so our goal will be to learn this graph structure from observing samples from these, the observed variables. Okay, so let me tell you just a little bit about this. So this can still be done using overcomplete ICA methods. And the only issue is that these methods don't guarantee that you converge to a global optimum. So you might not actually find the true parameters. So that's one way of learning this graph. Other methods can also learn this graph, but they don't learn multi-directed edges. They only learn bidirected edges. So basically, instead of learning this edge, which is a 3-directed edge, they will learn 3 bidirected edges here. Okay, so so this is sort of what people have been doing, and our contribution is to be able to actually learn the correct graph with multi-directed edges, and we're going to use high-order cumulant information to do that. Okay, so in the remainder of the talk, I will tell you about this. So let's see, in the last few minutes. Okay, so we're going to use cumulant information. So let me just tell you quickly what the cumulant is. So it's like a moment tensor. So if you have a random vector x, its moment tensor would be, let's say it's mean 0. Its moment tensor would have entries like this. And so a cumulant is very similar, but it's you have to transform the moments a little bit. So, and the time when they start differing is when k equals to 4. So up to the third moments and cumulants are equal if your vector has mean 0. But for the fourth cumulant tensor looks like this. So it's an order for d by d by d by d by d tensor. D is the number of entries of the vector, and it can be obtained by taking the moment and then subtracting some products of second moments. And if you look at this for Gaussian, this is 0 because its fourth moment is actually a function of the second moments. It's exactly this function. So the cumulant for a Gaussian, the fourth order cumulant, or the even order cumulants for a Gaussian would be 0. And so this is only interesting for non-Gaussian variables. And so what we were able to show is that if x comes from a linear non-Gaussian acyclic model with graph G, so this one has directed and multi-directed edges, then its cumulants will satisfy some equations. So the cumulant ck at entry I1 up to ik will be 0 if and only if there is no k trek between the vertices I1 up to ik. And so what is a k trek? It's basically a way to get, so it's like a fork that has directed paths up to all of the vertices I1 up to ik and has a common top. So it's a way to go to all of these vertices in the graph. And the top could be observed, or it could also be hidden. So there could be a multi-directed edge at the top, and then just these directed paths to all of the vertices I1 up to ik. So if this doesn't exist in the graph, then this cumulant is 0. And if the cumulant is 0, then generically this won't exist in the graph. So we can look at an empirical cumulant and check if it's 0. And if it's 0, then we would say, okay, this probably won't exist in the graph. And so here is just, I rewrote this theorem. So here's these two graphs again. And in the first case, the third order cumulant, entry 2, 3, 4, will be non-zero because there is a 3 trek between 2, 3, and 4, but it will be 0 in this case because there is no 3 trek between 2, 3, and 4 in this graph. And so this gives rise to an algorithm to learn the graph, to learn a graph with directed and multi-directed edges. And this is basically the last thing I want to say. So suppose now that we have data from a graph that has some hidden variables like this, and some of them might have more than 2 children. Okay, so let's say this is the graph. First, we're going to get samples from the observed variables. So in this case, 2, 3, 6, and 7. And these samples will be y1 up to yn. And so what we're going to do first is we're going to use existing methods. For example, this most recent one. This is a different paper by Wang and Dorkin, which learns the graph with directed and bidirected edges. Okay, so now it just doesn't learn the multi-directed edges, but it has directed and bidirected. And it also estimates the coefficient matrix lambda that comes from the directed part. Then what we're going to do is we're going to remove artificially the influence of the directed edges from our data. So we're going to take the data for each vector and sort of remove lambda transpose times this vector. So remove all direct effects from the directed edges. So it'll be like getting data from this graph that doesn't have directed edges at all. It only has the hidden variables. And then we're going to use our cumulant theorem from before, just checking if entries of the cumulant are 0, to identify which of these bidirected edges have to be merged together to get a multi-directed edge. So here we use a variant of the Kerbosch algorithm for learning maximal cliques in a graph. And then, so this will help us estimate H, the multi-directed edges, and then we're going to put it back together, the directed ones that we removed earlier, and we'll get this whole graph. So basically, what we've done is we've added onto the existing algorithms the possibility of merging together the bidirected edges that they find into multi-directed ones, because maybe the common cause is actually, all of these 3 variables have 1 common cause instead of 3 common causes in this case. Okay, and so we also have more equations that hold for these high order cumulants. We can actually show that a subdeterminant of the tensor vanishes if and only if certain combinatorial conditions are satisfied in the graph. And here by a determinant of a tensor, I mean the combinatorial hyperdeterminant, which is very similar to the determinant of a matrix, but you have to sum over all permutations of not just the second mode, but all of second through kth mode. So we can see when such equations vanish. But what would be really interesting would be to learn not just some equations that hold, but maybe all relationships that hold, and not just for graphs with hidden variables, but also graphs with cycles and hidden variables. Okay, so these are potentially hard problems. Okay, and this is all I had to say. Thanks.